Ready?
Yep.
Did it? Okay. All right, today we're going to focus on what I call vector fields and direction fields for systems of two first-order differential equations. And we're going to talk about it in the context of a predator-prey model. There's three kinds of interacting species models in general that people typically consider. One is predator-prey, where you have one animal eating the other. Second is cooperating species, where the species cooperate and they benefit each other. Third is competing species, where they are competing against each other. On the board here, I've got a predator-prey example from the book. R represents rabbits and F represents foxes. Foxes don't typically eat rabbits unless they're starving, but we go ahead and pretend they do anyway. So this equation is telling you how the growth rate of the rabbits is affected by their population R and also by the fox population F. And this equation tells you how the rate of change of the fox population is affected by the fox population as well as the rabbit population. In the absence of foxes, the rabbits follow a logistic model with a growth rate coefficient of 2, which would represent 200% growth per unit time in the situations where the rabbit population was small, which is of course not realistic, but it makes the numbers come out nice. Here the carrying capacity is 3. That could be 3,000 rabbits if the units were in thousands of rabbits. And this is the rabbit-fox interaction term. It negatively affects the growth rate of the rabbit population because of the negative sign there. In the presence of rabbits and foxes together, this term will be positive and conceivably could contribute to a negative growth rate for the rabbit population. Excuse me. For the fox population, you've got, in the absence of rabbits, you have an exponential decay. Like the rabbits are their only food source. By putting this term here with a plus sign, that's an interaction term that gives you a positive benefit to the fox population. This being positive could outweigh that negative to make the fox population grow. The first thing you want to do in such a situation, when you've got a system of equations like this, is you want to find equilibrium points, which correspond to equilibrium solutions. Instead of a phase line, we're going to have a phase plane, an RF plane, and solutions are going to be curves in that RF plane, showing how both capital R and capital F change over time. We want to find equilibrium points in that plane that represent distinct single points with unique coordinates representing equilibrium solutions for both R and F in how they depend on time. You want to set both of these equal to 0 and solve for R and F. Let me do the setting after I factor. If you can, you want to factor to help you solve it. There's an R term in both of those terms in the dRdt equation. So that can be factored out. What's left over, you go ahead and distribute the 2 through the parentheses here. You have 2 times 1 is 2, and 2 times negative R over 3 is minus 2/3 R. And then with the next thing, you've got an R term there. You've got what's left over after factoring is a negative F, like that. Now go to the second equation. There's a common factor of F that can be factored out. You can also factor out a 2 if you like, though that's not absolutely necessary. What's left over? You would have a negative sign here, giving you a negative 1 there. And a plus 2R is left over from the second term. Now let's set these equal to 0 to get a system of algebra equations that you want to solve for R and F simultaneously. Since these equations are nonlinear, there could be more than one solution, 2 or 3 solutions, for example. How many are there? It's a little tricky. I have to think carefully here. Certainly if R and F are both 0, then both of these expressions equal 0. So the point, we're after equilibrium points here. The point R comma F equals 0 comma 0 certainly is one equilibrium point, which makes good intuitive sense. No rabbits and foxes in this situation, in this setting. They're not going to be rabbits and foxes. We're not assuming they move into the region or move out. How else can both of these equations be 0 simultaneously? Well, if f is 0, that makes this equation 0, and then r could also be something to make this term 0 when f is 0, and that'll result in an equilibrium solution. If f is 0, r equals 0 makes this expression 0, but also, focus on this factor right there, plug in f equals 0, you get 2 minus 2/3 r is 0. Solve that for r first by adding 2/3 r to both sides, and then multiplying both sides by 3/2, and you get r equals 3. So the point 3, 0, r equals 3, f equals 0 is another equilibrium point. Are there more? If r equals 0, could f be non-zero to make the second expression equal to 0? No, it couldn't. So this choice that I made initially to make f 0 and see if there was a non-zero value for r to make that expression 0 doesn't work in this situation for the flip. What if r is 0? Can f be non-zero? No, it must be 0. I forgot to put a 0 here, by the way. However, both r and f could be non-zero, just like on the test. Both of those expressions could be 0, giving you a simultaneous set of linear equations, which we can write like this right here. I set both of these things equal to 0, and I did a little rearranging. In general, you might have r and f terms in both of the linear equations that are left. In this situation, it's a little easier. We just have an r term. We can easily solve this equation for r to get r equals 1/2. And then substitute that into this equation in place of r. 2/3 times 1/2 is 1/3. So you get 1/3 plus f equals 2. F will be 2 minus 1/3, which will be 5/3. Everything look good? Catch me if I make a mistake. It looks like 1/2 5/3 is another equilibrium point. So that's the first thing you want to do. Second thing you want to do is you want to start to draw solutions in the phase plane. You want to label it with your two dependent variables, in this case, again, capital R and capital F. And the easiest thing to do in this situation is to, well, first of all, plot the equilibrium points. 0, 0, 3, 0, and 1/2 5/3. Maybe right about here. And the next easiest thing to do is to think about what happens on each axis individually. What happens to the rabbit population in the absence of the foxes? What if f is 0 so that you're on the r-axis? Go back here. The rabbit population follows a logistic model. The equilibrium points for that are going to be 0 and 3. Ignore that part. And as with all such logistic models, the 0 one is going to be a sink, and the positive one is going to be a source. Oops, nope, other way around. 0 is going to be a source, and the positive value at 3 in this case is going to be a sink. You can double check that, by the way, by just thinking about the sign of ERDT. You can plug in points in between 0 and 3, for example, like 1. Excuse me, you're going to get a positive value for this expression here when r is 1. You could also try plugging in a value bigger than 3, like 4. 2 times 4 is 8. 1 minus 4/3 is negative 1/3. You get a negative value for the expression there. Solutions along that axis have to be decreasing toward 3. And for the fox population, along the vertical f-axis here, in the absence of rabbits, it's an exponential decay. So solutions have to go down towards 0. 0 has to be a sink. I'm drawing arrows on the other side of this first quadrant here, but that doesn't have any real-life application. It's only the first quadrant, excuse me, it's only the first quadrant that we're concerned about as far as applications go. But now the hard part. What goes in the first quadrant but not on the axes, besides that equilibrium point there? And at this point we need to use technology. Okay, we don't have any other techniques besides using technology to help us visualize what's going to go on. So let's use Mathematica. And let's go ahead and plug in defined functions that are going to represent the right-hand sides of these equations. So I'm going to call this f of capital R, capital F. Little f is the function. Capital R and capital F are going to be the inputs for this function. The second expression I'm going to call g of capital R, capital F. So I'll define these functions in Mathematica in the usual way, but they are functions of two variables, so I need two variables in here with a column between them. All right. F of R comma F is 2R times 1 minus R over 3 minus R times F. Don't put RF like that. That would be bad. That would make Mathematica think RF is a single variable. Either put a space or make sure you don't make a mistake. Make sure you put a star in there for multiplication. G is a function of capital R and capital F as well. It's negative 2 times capital F plus 4 times R times F. You don't need a star after the 4 there, but it doesn't hurt to put it. Okay, so these are the right-hand side functions. I'm going to define yet another function of these two variables, capital R and capital F. Oh, and I was going to call it capital F, but that would be a bad idea. Usually, the book calls this capital F. But because I've got a capital F, as a variable, I'm going to call it something different, like capital G. How about? This function is going to be a function that combines the little f and the little g into one function. But it's a different kind of function. It's a function with two outputs, so to speak, which is a little bit oxymoronic because you should have been told in the past that functions have single outputs. Well, okay, we're thinking of this expression as being a single output. And we're going to think of it as representing a vector. Most of you know about vectors. Anybody not know about vectors? Well, there could be somebody watching the video at least not knowing about vectors. We're going to think of the input as a point and the output as a vector. And we're going to call it a vector field. Those who are in multi know about vector fields. And when I write it by hand, I'm going to put a little half arrow above it. In the book, it's bold-faced. I could put a full arrow, but I'm just used to putting half arrows. It's a little quicker. When written by hand, in this book, it's typically written in one of two ways. Either as what's called a column vector, with an entry up here and an entry down there, or as, well, a row vector or a point. However, when we draw it, we're going to draw it as an arrow, not a point. The key thing is it's got two components. I could also write it with the I hat and J hat notation from physics, though we don't typically do that in this class. Actually, this column vector notation will be the most typical way I will write it in class. The little f is the first entry, the first component. G, little g, is the second entry or second component. And if I introduce yet another vector, I'm not going to bother writing it in row form. You'll see it in the book in that way. Call this other vector capital Y, whose entries or whose components are capital R and capital F, the variables capital F, capital R and capital F. Once I do that, once I make these two definitions, I can think of the system of two scalar equations as a single one vector equation. How do we do that? I write it like this. dy dt equals capital G of R comma F, or I could write Y, in fact, even. Don't let it bother you if I do that. Got a capital R and a capital F up there. I could have put a capital R and a capital F down here, just like I have here. But Y is a vector whose components are R and F. Here written as a column, here not. Don't let it bother you. Okay? If I don't warn you, if I was you, it would be the kind of thing that would bother me. So I'm saying those kind of things. Don't let it bother you that I'm writing it as a column here and a row here. Don't let it bother you that I'm writing it as a Y there. I didn't have to. I could have written it in R and F. The point I'm trying to make is I can write the system of differential equations, two scalar equations, as a single vector equation. And when you write it in this single vector equation form, not only does it have the benefit of being shorter to write, it's also got the benefit of emphasizing the geometric meaning of what's going to go on with the phase plane. dy dt is really going to represent the velocity vector of a solution curve. I could even call it v if I wanted to. The solution curve is going to be, solution curves are going to be parametric curves. In fact, if you look in the book on page 162, solution curves in this example end up looking about like this. That's a parametric curve in this phase plane. Parametric curve as in multivariable calculus kind of parametric curve. R of t comma f of t. There I'm writing it as a point. And you can imagine the solution as being a moving point. Parametric curve is getting traced out as time goes by. I could also call this y of t if I liked. Though here you really are thinking of it more as a point than a vector, though I will still use the vector notation. However, if I consider any moment in time and say at a particular moment in time I'm right there, I can calculate the velocity vector of the curve at that point. Parametric curves have velocity vectors. I'm not saying the velocity vector is related to rabbits and foxes moving, okay? It's not related to running rabbits and foxes and their velocity vectors. It's a velocity vector for the picture, for the parametric curve in the picture. It's the derivative of the point, the position vector in a sense. And when you draw velocity vectors for parametric curves at any given point, they always end up being tangent to the curve at that point and pointing in the direction of motion. This is real key what I'm saying here. So, what's the connection? The connection is the differential equation is saying find solution curves whose velocity vectors at any point, at any moment in time, equal the output of the vector field at that moment in time. Now, vectors are drawn as arrows. And they have what are called components. Again, these numbers are called components, a first component and a second component. For this particular vector that I drew, the first component is negative because the vector is pointing to the left. It's the displacement in this direction, a horizontal displacement, and it's a negative displacement because the vector points to the left. So for this example, at this point, at that moment in time, or at that point, whatever the moment in time is, that quantity is going to be negative. The second component is the vertical displacement, and because the vector is pointing up rather than down, that vertical displacement is positive. And at that particular point, that means the value of this function is going to be positive. Let's try some numbers into this here. So I can enter this stuff into Mathematica. And actually, by the way, it will be more convenient to define G slightly differently. to think of its input as a point. I'm going to emphasize that by putting curly braces around it. In Mathematica, both of these things are lists. Things inside curly braces are called lists in Mathematica. As far as how we interpret the meaning of these lists mathematically, we're going to think of that as being a point, and this as being a vector. Points have coordinates, vectors have components. They're very intimately related to each other. At any particular point, then, I can find the output of the vector field. Let's try to estimate it at the point I drew there on the board. That point, say, is the point 1, 2. Capital R equals 1, capital F equals 2. Assuming my drawing's not too far off, I hope the first component of the answer is negative and the second component is positive. It is. I can graph that vector in this phase plane. The most basic way to do that is with graphics and arrow. Make the arrow thick and red, for example. The syntax goes like this. Anytime you want to make an arrow in Mathematica, if you want it thick and red, at least this is the syntax. The first entry of this list inside the arrow has to be the starting point of the arrow. And the second entry after the comma has to be the ending point of the arrow. So if I'm talking about the arrow right here where I'm pretending this point is the point 1, 2, and this vector, which I think I'll write as a column vector, is the vector negative 2/3, 4. The first point, the starting point's got to be the point 1, 2. The ending point for the arrow, if you think about it carefully by thinking about what happens in relationship between these coordinates and these components, you've got to take the 1 and add the horizontal displacement, which is negative 2/3, to get positive 1/3 for the first coordinate of that point, and take the 2 and add the displacement in the y direction, which is positive 4. 2 plus 4 is 6. That's going to be the second coordinate of that point, which makes this drawing way off. Okay, it's going to be more like that. In Mathematica, I could go ahead and just type those in. 1, 2, and 1/3, comma 6. Like that. There it is. There's the arrow. You don't see the axes here. Maybe I should make it big, so it looks more like an arrow. You can see a small little arrowhead there at the top. I can put this within some axes, and I am going to do that pretty quickly. So I could certainly make it that way. However, you might say, well, I don't want to have to always figure out what that second point is. I don't want to always have to do this calculation, for example, and then add the components. I'd rather have Mathematica do it, so I could do it like this instead. 1, 2 plus g of 1, 2. That is adding vectors. You can also think of it as adding points. It's going to add coordinate by coordinate or component by component. It's going to take the 1 and add on the displacement of negative 2/3 to get 1/3. It'll take the 2 and add on the y displacement of 4 to get 6. And it will plot the same picture. Okay. Since you don't see the axes, you don't know for sure that it's the same vector, but it is. I could go ahead and see what this produces. Emphasize it is the point 1/3, comma 6. I'd like to make a bunch of these vectors, though. Just having one of them is not good enough. How can I make a bunch of these vectors? I can make it with VectorPlot. Now, we've used VectorPlot before to make slope fields. When we When we used it to make slope fields, we put a 1 in the first spot, and then the little f of y, or little f of t comma y in the second spot. Right-hand side of the differential equation. For systems of 2 equations, like this, first order system, you do not put a 1 in the first spot, you put the first component of the system, the right-hand side of the first equation in the first spot. You put the right-hand side of the second equation in the second spot. There we go. And now these, I didn't add a vector scale here. By default, it is making vectors in the vector field that point in the right direction at each given point and are scaled relative to each other to be, relatively speaking, the right lengths compared to each other. They're not as long as they actually should be. They're not as long as the actual vectors in the vector field. They are scaled down because if you make them as long as the vectors in the actual vector field, it becomes too messy. The picture becomes too messy. But relatively speaking, you know, this arrow looks maybe twice as long as this arrow. Hopefully that's the case with the actual vectors, but they'd be much longer. You can also make something called a direction field, where the arrows end up having all the same length. Now that's not true for the vector field. However, it does make the picture look even nicer. If you use the vector scale option and go 0.03, comma 1 instead of 0.03 again, comma none. Again, the details of why this work, I don't know. Why does this work? Well, it gives you a nice picture. Okay? These are the options that I end up using typically to get a nice picture. 0.03, comma 1, comma 9. So what's different compared to slope fields is this is a 1 instead of a 0.03. If I made it a 0.03, then you wouldn't see arrows anymore. You'd see just line segments. By making that a 1, I'm making them look like arrows. But it's not technically this is not the vector field anymore, not even a scaled down version of the vector field, because all these points, all these vectors have the same length. So it's called a direction field instead of a vector field. I mean, it is a vector field, but it's the direction field for the system. The only information it's telling you is the direction of solution curves, not the length, the velocity vector for the solution curve. So it's not telling you how fast the solution curve is getting traversed. Let's put a, I'm going to color these vectors a different color as well with vector style. Red. I'm going to combine this with another graph. You show it combined with another graph. The other graph I'm going to make is with a command called StreamPlot. And the syntax is going to be almost the same as for VectorPlot. I'm going to put the StreamPlot, I should probably put it in second. So I'm going to change the word vector to stream. I'm going to get rid of this vector scale option. I'm going to change the vector style option to stream style. And what color should I use for stream style? Green. How about blue? When I was in 8th grade, I took painting. Did I tell you about this story? I took painting in 8th grade. My teacher loved to just ridicule our paintings. And I made a painting of a fish jumping out of some water and a fisherman in the background fishing. And the teacher didn't like how darkly I colored my water blue. And he's like, "Kenny, what color's water?" And like, I'm not quite sure what to answer him. Why is he asking this? And so I don't say anything. He's like, "Kenny, what color's water? And by now he's that loud and the entire class is eagerly anticipating my answer. And I'm like, blue? And he's like, no! Water's clear! I'm like, well, I thought you wanted me to say something. Like, say an actual color. Blue. But he's like, it's clear. Actually, I got the last laugh, though he doesn't know about it. A few years ago, maybe it was Wikipedia, maybe it was something else more trustworthy. I saw that water actually does have a slight blue tint to it. So I'm like, yes! I was right. What in the world? Stream style blue. What's the StreamPlot going to do? It's going to create streamlines, which are solution curves. And here you're seeing what I kind of drew on the board there. You're seeing the spiraling behavior in toward that equilibrium point whose coordinates are at, what was it, 1/3, 6? Oh, no, sorry. 1/2, 5/3, 1/2, 5/3. I'm going to get rid of the frame and put axes in there as well. Frame, arrow false, axes, arrow true. The equilibrium point is at r equals 1/2, f equals 5/3. It's right about there. Whoops, moved on me. 1/2, 5/3. It's right about there. It's hard to tell. This curve is going to come back down, but you can't really tell. I should put the equilibrium points in the picture as well. That can be done with graphics and point, though I typically do it with ListPlot instead. ListPlot. Draw the equilibrium points 0, 0, 1/2, 5/3, and 3, 0. They're in there, though they're kind of hard to see. Let's color them black. There they are. There's your 3 equilibrium points. This one is some sort of spiraling sink, you might call it. This one, hard to know what to call that. It's going away along the r-axis and towards, the solutions are going toward it along the f-axis. They ultimately go away when they're not on the axes. So that ends up being called a saddle point. We'll call that a saddle point. This one's a saddle point too. Solutions are going toward it along the r-axis and away from it along some other curve about like that, and other solutions end up going away in this kind of manner. That will be a saddle point as well. The key thing to realize here is what's the main lesson about what this model is saying about rabbit and fox populations. It's saying that no matter where your initial condition is, no matter what the starting populations are for R and F, as long as you're off the axes up here, solution curves look like, well, once F gets high enough and R gets small enough, they head rapidly back down towards this equilibrium point eventually. It seems to be the case that ultimately the rabbit and fox population is going to go toward an equilibrium. Though the behavior, if you're over here, is kind of extreme initially. The rabbits almost die off and the fox population gets very large. But then the foxes don't have much food, and so they die off a lot. And then both the rabbit and fox population is low down here before they ultimately oscillate toward an equilibrium. Can I, excuse me. Can I draw any actual vectors from the vector field in here? Yeah, I can use graphics and arrow to draw actual vectors in the vector field. Let's copy and paste this code. There's an actual vector in the vector field. Probably colored something different. Magenta. much easier to see. At this point where this vector is based, the output of the vector field is this vector, which we already knew had components, looking back over there, what were they? Negative 2/3, 4. The horizontal displacement is negative 2/3. The vertical displacement is 4. As a solution curve comes around here and touches that point at a certain moment in time, that vector is the velocity vector for that solution curve at that moment in time. At that moment in time, the solution curve is moving with a direction that's in the same direction as this vector, and with a speed equal to the length of this vector. That's how velocity vectors work. And again, I'm not talking about rabbits and foxes running. I'm not talking about their velocities. I'm talking about, in this picture, the velocity of the solution curve at that point, in the picture. Okay, that's the key idea for understanding the phase plane, how you relate these two equations, and how this equation is telling you that the velocity vector of a solution curve at any moment in time, wherever it happens to be, it's at a point whose coordinates are y, is the output of the vector field at that point. That's the key insight for why this graph is telling you about solutions of a differential equation. Got a few minutes. I want to show you about Mathematica's built-in numerical differential equation solvers, NDSolve and NDSolveValue. They can find good approximations to actual solution curves, not formulas, but good approximations, essentially data, like Euler's method produces, and an interpolation method for how to connect the dots. NDSolveValue ends up being easier to use. Let's use it here. NDSolveValue is the numerical analog of DSolveValue. Capital N makes it a numerical algorithm here. I can type in the system of differential equations like this. Capital R prime of t equals equals. Now I could type the entire right-hand side that I had originally, or since I already defined the function little f, I can also use little f. But don't plug in R and capital F. Mathematica needs to know those are functions of t. You need to put t's in here. This is an autonomous system, by the way. There's no t's on the right-hand side. That's the first equation in the system. The second equation is capital F prime of t equals little g of r of t, comma, f of t. I need some initial conditions. Let's let r of 0 be 1 and f of 0 be 0.1. I need to put a comma next, then put the things I'm solving for, capital R and capital F next inside curly braces. Then don't just put a t, but instead put a list, t comma 0 comma some positive number, I'll try 10, representing the interval that you're approximating the solution over, the interval of time. I get output that looks funny. This output is hiding a lot of information. It is showing you approximate graphs of R and F individually as functions of time. Can we graph it in the phase plane? Let me do this to help me graph it in the phase plane. I'm going to create a new list set equal to the output of this. RSol and FSol stands for R solution and F solution. This is the thing, once I've entered this, that I can actually plot in the phase plane with parametric plot. Let's copy and paste this code here. Down here. And add in a parametric plot. Parametric plot. Because solution curves are parametric curves, R sol of t, comma F sol of t as t goes from 0 to 10, and let's go ahead and make it green. Plot style, big green. There's your solution curve, that NDSolveValue approximate. Before I put this on Moodle, I'll also put it inside of manipulate, where the right endpoint of the time interval I'll call b and let b go from 0.001 to 10, and you'll see the solution curve get traced out. And what I want you to notice once you've downloaded it is that the speed is not constant. There are places where it goes fast and goes slow. Okay? In fact, it's got to go slower and slower as it heads toward that equilibrium point overall. Okay? See you on Wednesday.